Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Dr. Josh Winn, who is a physicist and astronomer at Princeton University. His research goals are to explore the properties of planets around other stars, understand how planets form and evolve, and make progress on the age-old question of whether there are other planets capable of supporting life. His group uses optical telescopes to study exoplanetary systems, especially those in which the star and planet eclipse one another. Welcome, Josh.
Hello. Thank you for having me.
Sure. Yeah. So I want to use one of your older papers to sort of set the context for our conversation. And it's entitled The Occurrence and Architecture of Exoplanetary Systems, in which you say the basic geometry of the solar system, the shapes, spacings, and orientations of the planetary orbits has long been a subject of fascination as well as inspiration for planet formation theories. For exoplanetary systems, those same properties have only recently come into focus. So you wrote this paper in 2015, and I think there has been a lot of exoplanetary discoveries, I think, right? So
For sure.
what is the count now? How many exoplanets have we found so far?
I think the closest thing to an official count we have has about 4,500 exoplanets.
4,500. And it's all over the place. And in general, there is, I would imagine there's some limitations beyond which we cannot really find them, right? So,
Yes.
So could you sort of set the context for I know that there are 2-3 different methods by which we find them. Could you describe those and what's the sort of the maximum distance we can target to find an exoplanet? Yeah.
Yeah, you're right to begin with the technology because this is a very technology-driven field.
Yeah.
There have been speculations since the ancient Greeks about whether the other stars are like the sun and whether those stars have planets, and that seemed increasingly plausible as the centuries went on and we learned more and more astronomy. But it really wasn't until the mid-90s that this field of exoplanet science got going, and that's entirely because of limitations in our ability to perform the measurements.
Yeah.
And so the measurements are, well, the first thing you might think of doing if you want to find a planet going around another star is to use some big telescope and make an image of the star and then look for the little dots going around the star. That's a very direct method. And unfortunately, it's also extremely difficult. And it has worked, but only barely in a few cases where you can actually see the planet as a little dot of its own.
What's the distance approximately where we can actually image a planet?
The distance from us?
From us, yeah.
So how do we reckon distances? One way to measure distances is in light years, distance that light travels in a year. And the nearest stars are a few, let's say, 4 to 10 light years away.
Yeah.
And most of the exoplanets we know about are within a few thousand light years, and with more being known closer to us than farther away. And that's, again, for practical reasons. It's much easier to perform the necessary measurements if you have a bright star and then a nearby star. So we quickly lose the ability to detect planets if they're all the way across the galaxy. We have very little hope of that. We're really exploring our tiny little neighborhood of the galaxy.
But even 1,000 light years, so we can actually image a planet at that distance?
I think the ones that have been imaged are closer than that, maybe 5,200 light years, although I would have to look it up to be sure, maybe several hundred. Okay. I don't know if that sounds like a lot or a little to you. To most ordinary non-scientists, it's a tremendous distance. Like, it's an almost unfathomably mind-boggling distance.
Yeah.
But to an astronomer, that is really next door. There are astronomers who study things that are many, many times farther away.
Yeah, so I was just sort of looking at the finding an image at that distance from an Earth-based telescope is really challenging.
It is. Yes.
Now the biggest issue is the star itself, right? The star is so bright.
That's right.
Anything that surrounds it becomes very difficult. So I know that there are some techniques that allows you to actually fade out the light coming from the star to actually see the planets. Is that possible?
Yes. So the basic problem is that we cannot focus our images as tightly as we might want. And some of that is baked into the laws of optics. That is this phenomenon called diffraction, that whenever you interrupt a light wave with a telescope, say, then the light wave develops curvature. And the result of that is a blurring of the image in your camera. And so that's kind of an irreducible problem. And it means that if there is a tiny little dot right next to the star, then the blurring of the star will overlap the dot from the planet, and we won't be able to see it. Right. So one approach is to just make tighter and tighter images, and one way to do that is to have larger and larger telescopes, because the blurring effect, in principle, goes down with larger telescopes. Another way is to put your telescope in space, where it is possible to make sharper images than on the ground, because on the ground, in addition to the problems with optics and diffraction, you have the atmosphere, which is constantly messing up the paths of light rays and causing additional blurring in our images. But then what you alluded to is there are special cameras you can build that manage to zero out the light from a very specific point in the image, which you align with the star, and thereby allow the surrounding area to be searched without the severe problems of the glare from the star. Those instruments are very advanced and finicky and high tech. Most of them go by the name of a coronagraph, because these same kinds of instruments were originally used to image the corona, the outer layers of the sun, by blocking the sun's glare. And they basically work by putting a carefully designed obstruction, actually two obstructions of different shapes, within the light path, so as to block the light and direct the light from a star to other areas of the instrument and prevent it from reaching the detector.
Right. Yeah, I mean, the beauty of seeing an exoplanet actually revolve around a star in itself is a magnificent thing. Yes. But we have a couple of other techniques to not to see them, but at least to sort of speculate they exist.
Yeah, right? To deduce they exist, basically.
To reduce.
Yeah. So before we leave the topic of this imaging method, though, I want to direct your listeners to a particular video that I think every human being should watch. You need to look up the name of the star. It's HR8799. It doesn't have a very glamorous name, but on YouTube and elsewhere, you will find a movie of 4 planets as tiny little dots circling around at least a small portion of their orbits around this nearby star. So that has been the greatest success of this direct imaging method so far.
And how far is it? How far is HR8799?
Yeah, I will look that up as we speak, but it will take just a moment. It is 130 light years away.
130 light years. Okay. Yeah. And so just to set context, the nearest star or nearest star that we can see is Alpha Centauri.
That's right. And Alpha Centauri, in fact, there are 3 stars in that system. They're all about, I think it's 4.3 light years away.
Just 4.3 light years away. So we have some stars that we can see by naked eye a few light years away. And the closest one we cannot see because it's too dim, right?
Yeah, that's the interesting thing. When you look at the night sky without a telescope, with just your eyes, you see, 1,000 or so bright stars, but those are not the nearest stars. What happens is stars have a wide range of brightnesses, of luminosities, and some stars are tens of thousands of times more luminous than the sun. And so you can see those things much farther away than you would be able to see a sun-like star. And in fact, that's what most of the stars in the sky are. They're these overluminous giant stars. The most common kind of star, like you said, is a tiny little red dwarf star that might have 1/10,000th of the luminosity of the sun. And they're very common. They outnumber sun-like stars, but we can hardly see any with our naked eyes. In fact, I think there might be a few that we could see with the naked eye, but they do not call attention to themselves.
Mm-hmm. And so HR 8799 is something that people look up on YouTube and elsewhere. And so that's one technique that was used. Many parameters have to fall in place for that to work. But there are more common methods that you use to identify exoplanets. Right?
Yes. In fact, most of the great majority of those 4,500 known exoplanets came from two different methods, not imaging. And as you said before, those methods are more indirect. We do not see the planet. We do not receive any light from the planet that we can distinguish, but we track the light from the star as precisely as possible. And we use that and our knowledge of physics to deduce the existence of the planet. And in fact, sometimes we can make a lot of progress. We can even measure the mass and the size of the planet to within a few percent, even though we can't see it. Let me explain. Right. So the method that's conceptually the simplest is based on eclipses. When the moon goes in front of the sun, we get a really dramatic solar eclipse and the sky goes dark for a little while. But sometimes Venus or Mercury will pass in front of the sun and nothing really happens. You have to be told by an astronomer that it's taking place because you would never notice. And that's because Venus or Mercury only block a small percentage of the sun's light.
Yeah.
But we are getting really good at monitoring the brightnesses of stars precisely. And so if something like that were to happen to a distant star, we can tell. So that's the idea, is that you wait for a planet's orbit to carry it directly in front of the star as viewed from our position in the galaxy. And then you notice that the star appears to get slightly fainter.
Right. Yeah. To make it practical, you need the star to move at some reasonable speed, right? So you have to measure before the star is in front of before the planet is in front of the star and afterward. Right. And so the orbital durations, I think it's going to be important. for that measurement to take place.
That's right. So if you were looking back at the sun from 100 light years away, from some alien planet with telescopes similar to ours, and if you were in just the right place to see the Earth cross in front of the sun, what would happen? First of all, it happens once a year. So you have to be monitoring it pretty continuously in order to catch it happening. It only lasts for, I think it's like 10 or 12 hours. And during that event, you would see the sun get fainter by about 100 parts per million. So a relatively small amount. So that's the game. You look for these short duration dimming events by monitoring hundreds of thousands of stars, or as many as you can, as precisely and as continuously as possible.
So what is sort of the distribution, Josh, of that 4,500? I don't know if you have it handy, but so what's the maximum orbital duration we have, and what's the minimum?
Right. So the methods that we have are best at picking up planets that are on very close orbits, very tight orbits around the star, with short orbital periods. The period is the time it takes to go all the way around. And so most of the planets we know about have orbital periods shorter than a month or 2 months. And that's kind of remarkable. We didn't know that such planets would exist. In the solar system, the closest planet to the sun is Mercury. And Mercury takes 88 days to go around. And we used to think that was pretty close. Mercury was pretty hot.
Right, yeah.
Most of the planets that we have available to study now are much closer to their stars than Mercury is to the sun. Some of them have orbital periods of just a day, or even, I think the record holder is about 5 hours. So there are planets that are about as close as it is physically possible to be to their star.
Yeah, so these variables are related, right? So the orbital period, the distance from the star, the mass of the planet, and the mass of the star, they're all sort of related.
Well, the three things that are linked are the mass of the star, the orbital distance of the planet, and the orbital period of the planet. They are linked. They are linked through Kepler's third law. It's one of Kepler's laws of planetary motion. And it basically says that if you're farther away from a star, then the orbital circumference is larger, and the orbital speed is also slower because there's less gravitational force pulling on the planet. And both of those things together make the orbital period longer.
Right. Okay. So in this is called the transit method, right? The one that you described. So what happens if there are sort of multiple planets going around, and they could sort of influence each other, right? So what will we see if there are, let's say, 4 different planets in tight orbits around the star?
If the planets' orbits are very aligned with each other, so they form a flat system like the solar system, and if we are lucky enough to be viewing that plane edge on, so that we see all the planets go right in front of the star, and what we see is lots of dimming events. Each planet produces dimming events on a different schedule. So our brightness record will have traces of all of the planets. I think the record holder right now has 8 of these eclipsing planets. We call them transits because the term in astronomy for when an eclipse is occurring and the body in front is really small compared to the body in back, we call that a transit.
Okay. So we know these things exist. At least 4,500 of them have been found and named, so to speak, at least by numbers. And technology is advancing. So are we in a position to sort of characterize them, their composition, if they have atmosphere? And ultimately, one of the nagging questions still remains to be if there is life out there.
Absolutely. So that was a whole bunch of questions. Let's try and go through them. So you asked about what have we actually learned? What do our methods tell us about each planet? And one thing is the planet's size. And that we can get if the planet is a transiting planet from the amount of light that it blocks. The amount of light that it blocks is simply the size or the area of the planet's silhouette divided by the area of the whole star as it appears in the sky. So for example, if it's a sun-like star and we see the brightness go down 100 parts per million, it's going to be an Earth-sized planet. If it were to go down by 1%, a much larger signal, that would be a giant planet like Jupiter. Now, the next thing we want to learn is the mass, because that's kind of the first thing you want to know about a planet. It tells you the density if you have both of those quantities. It tells you whether you have a rocky planet or a gaseous planet or something in between. To get the mass, we have to use the second planet finding technique, the one I haven't described yet. And that's called the Doppler method. And it's based on the Doppler effect, which some of your listeners might know, some of them might not. The Doppler effect is a shift in the wavelength that is observed whenever the source of the waves is moving. So in the world of sound, for example, when an ambulance is coming towards you and then zips away from you, you hear, and that's because as it's coming towards you, the sound waves produced by the ambulance are compressed, and shorter wavelength means a higher pitch. And then when the ambulance zips away, the waves are stretched to longer sizes, and that corresponds to lower pitch. Same thing happens for any type of wave, including light. So when a star is, well, even when an ambulance is coming towards us, the light from the ambulance the light waves are slightly compressed. And so the ambulance would appear slightly bluer. Shorter wavelengths means bluer for light. And when it's receding, it should look slightly red. We never notice that, of course, and that's because the effect is minuscule. The fractional change in the wavelengths is the speed of the object divided by the speed of light. And that's usually very, very small. But for stars, they're moving pretty fast sometimes, and we've gotten very good at measuring these tiny, tiny shifts in wavelengths. So we can actually tell when a star is moving and how fast. And that's our way in, because we always say the planet orbits the star, but really it's slightly more complicated. Both the planet and the star orbit the center of mass of a planetary system. So the center of mass is close to, but not right at the center of the star. The center of mass is kind of like the average position of all of the atoms in the system. So,
yeah, it's typically, I would imagine, given the size of the star, it would be typically inside
the
star.
For the solar system, the center of mass is usually just outside the surface of the sun, but not so far. So it depends on the masses of the planets and on their orbital distances. Yeah. But it's like in that case, it's close to the center of the star, but it's not right at the center. And so the sun wobbles around in response to the gravitational pull of all of the planets. So it's doing a complicated little dance because all the planets are moving around and pulling it in different directions. And that's what gives us our way in, because when we see, using the Doppler effect, that some other star is wobbling around, then if the wobble has the right characteristics, we can deduce there must be a planet or several planets going around. And we can measure the orbital periods of those planets. And we can learn the shapes of their orbits. And we can learn, if the planet is also a transiting planet, we can learn its mass.
Right. Wouldn't you need sort of an estimate of the star's mass?
So in all of these cases, we can only learn about the planet to the degree that we know about the star. If we're uncertain of the star's mass, we will be equally uncertain of the planet's mass.
Yeah. And so how do we typically estimate the mass of the star?
Yeah, that's a difficult problem. The best way we have in astronomy for measuring the mass of anything is to see it move under the influence of gravity. Like That's how you can measure the mass of the sun, for example, if you watch the planets go around and you measure their orbital distances and periods. But if a star is just sitting there and there's no other star that is pulling it around, we don't have that way to measure the star's mass. And so we have to make an educated guess based on the appearance of the star, its color, its luminosity, and other observable characteristics.
Okay. And so that's an estimate that gives us sort of an estimate of the mass
Yes.
of the planet. And then that should tell us at least approximately what the composition
Yes, so
might
if
be.
we are lucky enough to see transits and to detect the star's motion, we get the mass and the size. We can calculate a density. And if it comes out to be 5 or 6 grams per cubic centimeter, well, that's just like the Earth. If it comes out to be 1 gram per cubic centimeter, that's more like Jupiter and Saturn that are mostly made out of hydrogen and helium gas and are much less dense. Now, the interesting thing is that, so we have found planets that have the same density as the Earth, and we've found planets just like Jupiter and Saturn. We've also found planets that are hundreds of times denser than the Earth, and we found planets that are, let me get this right, that are 20 times less dense than Jupiter and Saturn. So there's a humongous range of types of planets that we are seeing compared to the sample that we have in the solar system.
Hundreds of times denser than the Earth means it's some sort of metallic.
Well, it's even beyond that. I think so. As you get those objects that are so dense are also very massive, and so they're kind of borderline stars. Some people call them brown dwarfs. And the reason that they're so dense is that they're not quite massive enough to ignite nuclear fusion in their centers like stars do. And that means that they don't have that source of heat and pressure that would cause it to expand and become a star. So the only thing that's holding it up are material forces and then this other strange quantum mechanical effect called degeneracy pressure. The resistance of material to being compressed purely due to the quantum mechanical need for particles not to occupy the same state. So it's a very strange type of matter that is would be hard or impossible to reproduce in a laboratory on the Earth.
And the third aspect that I think we are getting an increasingly better view is the atmosphere, right? So how do we understand what might be if it has an atmosphere, first of all, and then if it is, what the composition?
Yeah, you're right. The remarkable thing is that we can learn anything at all about the planet's atmosphere. We can't see the planet, right? How can we possibly know what's in its atmosphere? Right. And the trick relies on eclipses. Well, I should say first, in those lucky cases like HR 8799, where we have seen separately the star and the planet in an image, we can obtain a spectrum of the planet. That is, we can take the light from the planet, spread it out into thousands of different colors using a prism or a grating, and then analyze the intensity at each color, and thereby learn something about the composition of the atmosphere. Because different atoms and molecules will absorb light at very specific colors. So if we see these dark features in the spectrum of a planet's light, we can deduce what must be in the outer atmosphere of that planet.
So we'll take a spectrum before the transit, take a spectrum after the transit, and sort of.
So I was talking about the directly imaged case where you just take a spectrum of the planet, but you are right that you can perform the same kind of trick with a transiting planet, even though you can't see the planet. Like you said, you perform spectroscopy spanning a transit. And if you see a little bit of extra absorption at specific wavelengths during the transit, you can probably attribute that to absorption as the light passes through the planet's outer atmosphere before proceeding all the way to the Earth. So we have little glimpses of the atmospheres of some of these exoplanets in the most favorable cases.
Okay. And so of the 4,500 we have, how many of them pass the test, George, in terms of they have to be, sort of at the right distance, sometimes called the habitable zone, so that they can harbor water. We believe oxygen has to be there for life to thrive. So how many of the 4,500 sort of pass the test for all of those characteristics?
Well, it all depends on how strict you want to be. We don't exactly know. We don't have a theory for life, really. We don't know what are the necessary conditions, or even what are the sufficient conditions. We don't know how life got started here on the Earth, after all. So we don't know exactly what to require to count the planet as habitable or anything like that. So we just have a working definition. And the working definition is it's probably got to have a solid surface. So that rules out Jupiter-like planets, at least for now. And it probably would be good if there were liquid water oceans on the planet's surface. And that's simply because all the life we know of on the Earth involves water in some way or another. We think life got started in the oceans. And so maybe, and there are some theoretical arguments that people have made that water is especially good for creating a haven for complex chemical reaction networks. All that aside, it's what we have. So maybe we should prioritize planets where liquid water would possibly pool up on the surface. And so that restricts you to a range of orbital of temperatures for the surface. It has to be between the freezing and boiling points of water. And that, in turn, restricts us to a certain range of distances from the star. And that's the so-called habitable zone.
And distance is a function of the star's characteristic, right? So if you have a red dwarf or something like that, so the luminosity of the star would drive. So
in our solar system, of course, the Earth is in the habitable zone. But if you were to crank up the sun's luminosity by a factor of 100, we would have to move 10 times farther out in order to stay at the same temperature. So the habitable zones of luminous stars are in wider orbits. Likewise, these really, really common red dwarfs that I mentioned earlier, you have to be really close to those to be as warm as we are. And so the habitable zone occurs at much smaller orbital distances.
Right. So density and temperature, at least from a working definition perspective, are things that we look at. So of the 4,500, I think there are many candidates.
Well, I wouldn't say many. They're very difficult to detect. The rocky planets, we've learned, tend to be small compared to the gaseous planets. And that just makes the signals harder to detect. And at least for sun-like stars, the habitable zone corresponds to a period of a year. And that means you have to monitor these stars for many years to be really sure that you know what you're talking about with this planet. And all of that together means there are really only maybe on the order of a dozen credible contenders for habitable planets these days. Also, a lot depends on how willing you are to accept a red dwarf as a possible home for life. People, even if you're in the habitable zone of a red dwarf, so you're at the right temperature, it's kind of questionable whether most of the light of a red dwarf comes out in the infrared range of the spectrum rather than the optical. And so that makes it hard to drive certain chemical reactions, like photosynthesis, for example, would have to be quite different around a red dwarf star. And there are other properties of those stars that make them seemingly less hospitable. They have much more frequent flares of high energy radiation than the sun does, for example. That seems kind of bad for life. So, if you include the red dwarf stars, we have more than just a dozen habitable planets, but it's debatable whether those should count.
So there are two ways to go, right? If you take Earth as a proxy for a habitable place, then you have to look for Earth-like systems around.
And we have zero of those. There are no places we know of where we've been able to detect an Earth-sized planet in a 1-year orbit around a sun-like star. That remains a goal for the future.
Right. So in some sense, this is probably too early. In some sense, this sort of says that, the Fermi paradox that people talk about, that we haven't found any life out there. It's not too far-fetched, right? I mean, it is difficult to get conditions exactly right.
Well, it's important to distinguish what we're able to detect from what's actually out there. We are struggling to detect Earth-like planets because of the limitations in our technology, but we have every reason to think that they're very common. And that's just from extrapolating the results we do have for somewhat larger planets, somewhat closer orbiting planets. If we just extrapolate mildly out to the location of Earth-like planets and sizes of Earth-like planets, they should be quite common. In fact, there was a study published just a few days ago announcing the results from a big NASA mission called Kepler that has taken many years to prepare, that finds that something on the order of a quarter of sun-like stars have potentially habitable planets by this working definition.
A quarter of a sun-like star. So how many sun-like stars do we have in the Milky Way galaxy?
I think there's a total of about 100 billion stars, of which maybe 10% could be plausibly called sun-like.
Yeah, so it's still a huge number in just one galaxy. And
so my point of view is that the numbers are so high, so extreme, that surely there is nothing unique or special about the sun and the Earth. And undoubtedly, there are other planets that resemble the Earth almost as closely as we might want, if we are willing to look far enough away. And so, it seems the Fermi paradox remains in that sense, that if life arises commonly and proceeds to advanced civilizations commonly, then there has been enough time since the Big Bang and the formation of our galaxy for those civilizations to have crisscrossed all over the galaxy, visiting everywhere. And so, where are they? That's the Fermi paradox. And I don't think that exoplanet science has resolved it. We are finding that there appear to be plenty of locations. There are plenty of planets that have at least plausible properties, similar enough to the Earth that it makes you wonder.
We'll take a quick break, George. When we come back, we'll talk about Kepler 78. Okay. Dr. Sun. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Josh, we have been talking about exoplanets. That is planets around stars outside the sun, and talking about how to detect them, how to measure them, their mass, their composition, their density, their distance from their stars, their orbital periods, and so on. And this has been an ongoing pursuit by many in the last 20 years, and we have over 4,500 identified exoplanets out there. But they all have very, very different characteristics. And you have a recent review article, Kepler 78 and the ultra-short period planets. So this is an exoplanet named Kepler 78b. I guess it was discovered by Kepler data. And it's about the size of the Earth, but its orbital period is 8.5 hours. So that seems really, really fast. You want to talk a bit about that?
Sure. Maybe I could back up and say that this was one of the biggest surprises of exoplanet science. that you can have planets that orbit their stars much more closely than any of the planets orbit the sun. And Kepler-78 is one of the more extreme examples of that phenomenon. But in fact, the Nobel Prize in Physics last year was awarded, at least half of it was awarded, to two of the exoplanet pioneers, Michel Mayor and Didier Queloz, because they discovered a giant planet similar in size to Jupiter, but instead of taking, 10 years or so to go around like a giant planets in the solar system, it goes around every few days.
Wow. Yeah.
And what we found is that those are kind of rare, that if you pick a random sun-like star, there's only maybe a 0.5% chance that it will have one of these so-called hot Jupiters. But 0.5% is not negligible. And the interesting thing is that we don't know how they got there. We had this very nice theory for planet formation prior to the discovery of exoplanets that predicted you should never find a giant planet so close to a star, that there's no physical way it could have formed there. So that's been part of the fun of this field. We were talking before the break about the search for Earth-like planets, and that is very exciting. But the here and now of this field are the really weird, un-Earth-like planets, and that's what's keeping us busy most of the time.
So the reason we don't expect such big planet really close to the star is that there isn't enough material. We can't really figure out how that much material will be there.
It's kind of a complicated story. One way of viewing it is that the solar system seems neatly organized with the rocky planets on the inside, that is Mercury, Venus, Earth, Mars. Then there's a gap, and then you have Jupiter, Saturn, Uranus, and Neptune, the gas giants. So just from that fact alone, it would make you expect that that's normal, that you should see giant planets beyond a certain distance and rocky planets within a certain distance. And so that's just an empirical fact and a pattern. But then what happened is, in the centuries over which people knew these facts, they developed theories that accounted for them. And the modern theory of planet formation came out of that work. It was not informed at all by exoplanets, since we didn't know of any. And that theory explained why it was inevitable that giant planets could only form beyond the distance of Mars. Now, the reason is rather complex. Okay, so I can try to explain it. I'm not sure how much detail to go into, because clearly there's something wrong with the theory, but let me try anyways. So in this theory, the rocky planets form first. And the way that happens is that there's a swirling disk of gas that surrounds a young star. It's basically a vortex of material that is slowly making its way down and crashing onto the star. And that's an outcome of the collapse of a much larger cloud that eventually led to the formation of stars. That's how stars are formed. And after they're formed, they're still surrounded by these swirling disks that we call protoplanetary disks. And they're mostly hydrogen and helium. Almost all the mass is hydrogen and helium, but at the level of a few percent, there are other elements like carbon and iron and nickel and silicon and so forth. And what happens is those heavier elements settle down into a thin layer in the midplane of this disk. And that's where they start to encounter one another. The density gets high enough that these particles of silicon and iron and so forth knock into each other, and they sometimes stick. And so you build up larger and larger pebbles and rocks and then boulders, and then in the story, you eventually work your way all the way up to the size of a rocky planet. There are some parts of that story that are a little hazy. We don't know. It's a long way to go to get from a speck of dust to an Earth-sized planet. But that is the current thinking.
But if there is hydrogen and helium there, George, when it gets to some size, wouldn't it start attracting the gas?
So the reason that doesn't happen at first is because the gas particles are lighter and they're moving around faster at a given temperature. And so they're harder to capture gravitationally. They just stay as this extended gas. It's only when you manage to build up a rocky planet that is massive enough to be able to start capturing with its gravity the surrounding gas. And that's, in this theory, that's a threshold process. That only happens when you accumulate a planet that's around 10 times the mass of the Earth. If you manage to build a rocky planet that big, then quite quickly it sucks up all of the surrounding gas and swells up to become a giant planet. And supposedly that is where the giant planets come from. So you form a rocky body, and then that becomes the nucleus of what will become a giant planet.
So that's possible, right? So instead of Venus and Mercury and Earth and Mars, maybe it all sort of jumbled together into a singular planet. Then that becomes big enough to start creating a gas giant.
It's difficult even when you have a bunch of planets and you let them collide in the inner solar system. It's difficult to get up to 10 Earth masses. There just isn't a whole lot of there isn't enough material and enough opportunities to accumulate. But what happens is if you go far out, away from the sun, now it's cold enough for a lot of common molecules like water and methane and ammonia to exist in their frozen forms instead of gaseous form. And so you have a lot more solid material out there than you do close to the sun. And that means it's easier to grow a larger solid body. So that's the way this theory works, is if you're beyond the so-called snow line, that is where you're far enough from the sun that water would exist in solid form, then you have more snow that you can pack onto one of these growing planets. And it's easier to achieve that critical mass of 10 Earth masses. And then you get promoted and become a giant planet. So that's how this theory explains why the giant planets do exist and should only exist in the far reaches of the solar system.
Right. Okay. And so that is the issue when we see these hot Jupiters, which are not rare, right? It's frequent enough to challenge the conventional theory.
Yeah, they're rare, but they're not complete freaks. The galaxy still has many millions of them. Right. So clearly there's something wrong with this theory or something missing. And the way theorists have reacted is interesting. They have not said, let's tear up this theory and start fresh. The reaction has been more like, well, everything was correct, what we said before. It's just that we didn't really think about what might happen after the giant planet forms. And there are a lot of things that could happen. For example, maybe you form 2 or 3 giant planets, but they're close to each other. And over billions of years, they have close encounters with one another. And that can cause them to one planet might get ejected and the other planet might take on a highly misshapen orbit compared to its original circular orbit that takes it very close to the star. And so that's just one example of other chapters to be added to the story that might cause a planet to take up a smaller orbit.
So some sort of migration process. So they formed out there, but ultimately it migrated toward the star, perhaps as an after effect of an ejection process. But whatever the process is, the theory sort of remains in the sense that they are not formed close to the star, but arguing that they are getting closer to the star because of some other process.
That's right. You add on a chapter at the end of the story to bring the planet close to the star.
Right. And when we find them, these hot Jupiters, they don't look normal, right? In the sense that, it's not a very, very, very stable orbit. There are other characteristics that seem to indicate that there's something unusual that went on.
Well, the main thing is they're hot. We should. That's the main way in which they're definitely different from Jupiter. Their temperatures are measured in thousands of degrees, as opposed to Jupiter, which is several hundred degrees centigrade below zero. I think
that is just the proximity to the star, though,
it's heated,
right?
it's roasted on one side by the star.
Yeah.
Their orbits turn out to be pretty stable for the most part. That is, we don't know how they got there, but at the moment, in most cases, there's nothing that would cause it to be destroyed. So they can happily orbit the star in such close proximity for billions more years. There's at least one exception, though. There's a hot Jupiter called WASP-12, and it is one of the closest of the hot Jupiters, one of the hottest of the hot. And we have seen that its orbital distance is very slowly shrinking. And that's because it's a transiting planet, and we can, every time the planet comes around and makes a transit, we time it. And the interval between the transits is getting shorter and shorter and shorter. I think it's by something like tens of milliseconds per year. So it's a tiny change, but measurable. And what that means is that in a few million years, if this continues, the planet will fall onto the star and be destroyed.
Right. So going back to the 4500, Josh. So, given I know that you do a lot of research in this area, so let me ask you, in conclusion, if you look forward 5-10 years, technology is improving quite a bit. I'm sure we're going to see a lot more than 4500 in 5-10 years. There are two major questions, right? One is about life, which may not be solved for a long time, and the other is about planetary formation and the theories around that. Do you anticipate those planetary formation theories to be sort of redone based on
it's
the data
already
we might
happening.
get?
The whole theory of planet formation has attracted so much more attention and is so much more exciting than it used to be, and is drawing in a lot of our young, most intelligent theorists because of all of the puzzles that the new exoplanet discoveries have presented. Not just the close-in planets, but there are some other really weird systems too. There are planets that orbit two stars at once. So they're like Tatooine, where you have a double sunset if you're standing on the surface of such a planet. There are planets where there are two planets that almost share the same orbit. They're extremely close to each other. And we don't know how that happened. It seems like a very delicate arrangement. There are planets that are revolving around the star backwards compared to the way the star is rotating. So that's also very strange. The sun is not like that at all. So yeah, planet formation is already being revised. And as we continue developing the ability to measure smaller planets, wider orbiting planets, and planets around a variety of different kinds of stars, then we will simply have a lot more data, a lot more range in our measurements to be able to understand what happened, how these planets came to be.
Yeah, I guess one complication is you need to know the history of the system, right? So, there could be a visitor of some sort into that system, and it could completely tear that apart and create configurations that are not evolved from the initial aspects, right? So we can't really predict that or speculate on that unless you know the history.
Historical questions are always the hardest ones. We can make very precise measurements of what's going on right now, but to deduce what must have happened billions of years ago, well, it's like paleontology. Our clues are fragmentary. There's no way to be sure. However, in this case, we're actually in a better situation than paleontology. Paleontologists, no matter how hard they look, cannot find a living dinosaur. They just do this. But if we look hard, we can find very young stars and observe them with our telescopes. So we can find stars that are still surrounded by these protoplanetary disks. And we can measure their properties and confirm that they're mostly hydrogen and helium gas with a little bit of heavy elements. We can measure the thickness of these disks. And in some cases, we even see features in these disks that could be produced by new forming planets. That is, we see ripples in the disks or gaps in these disks that might be the locations of newly formed planets.
Yeah, I want to ask you one more question, Josh. What is your view on? There's a lot of talk around Planet
Ah,
Nine.
yeah.
What is
Oh
your view
gosh,
on
I really
that?
hope it exists. So yeah, Planet Nine is this wonderful hypothesis that there is an
Yeah,
undiscovered, relatively large planet lurking in the outer reaches of our solar system. So it's not an exoplanet; it's an endoplanet, if you want to call it. It's one of ours,
right.
and it
Yeah.
would be beyond, well beyond, the orbits of even Pluto and Neptune. And the reason we have
Mm.
the reason why this hypothesis was proposed is that Pluto is one of a lot of objects that are far out there called Kuiper Belt objects, these tiny little asteroid-like
Yeah.
objects that seem to be left over from the protoplanetary disk that never really got it together to form planets. And there are patterns in the orbits of some of those Kuiper Belt objects. There's a small subset that have orbits that are unusually wide and that are also
Yeah.
aligned with each other. So the orbits are not circles, they're ellipses, and the ellipses tend to be aligned more often than you would think by chance. And you could just say, well, that's weird. I don't know. That just could be a fluke. But what Mike Brown and Konstantin Batygin of Caltech have proposed is that it's actually because there is a distant Planet 9 that's 10 times the mass of the Earth and is orbiting at hundreds of times farther out than the Earth. And what they have shown, theoretically, is that the gravity from such a planet could organize the Kuiper Belt objects into the pattern that we see.
Right. Right. It is really way out there, right? 300
That's right.
astronomical
That's
units or
why
something
it
like
might
that.
have been
Yeah.
undetected until now. It'll be very cold, very dark, and hard to spot.
Yeah. I guess none of the techniques that we described would be useful in this
Yeah, it sounds crazy
detection.
that we can detect a 10 Earth-mass planet around another star, but not in our own solar system.
Yeah.
And that's because, we don't have the anchor. We don't have the way in that we do with exoplanets. We can't measure the Doppler shift of anything and detect this planet. The way it will be detected
Right.
is the old-fashioned way of just searching the sky with wide field cameras, looking for any faint little dots that are moving the way planets should move and not stars. That's how Pluto was detected. That's how Neptune was detected. And there are astronomers at the moment who are doing the same thing, trying to seek evidence for Planet 9. You see, the problem with this theory, this hypothesis, is it tells you the mass of the planet, it tells you the orbital distance, but it doesn't tell you where to point your telescope. It doesn't say exactly where on the sky it should appear. And so you have to do a lot of searching.
Yeah. Yeah, it's going around. So it's this is one of those situations that perspective actually helps you a lot, right? So when you look to another system or another galaxy, you have a much better perspective than looking out from
True.
our own.
It's a good way to view the
our
entire
own system.
field as of exoplanets. It's helping us gain perspective on our own home.
Right. Excellent. Yeah, this has been great, Josh. Thanks so
Pleasure.
much
Always
for
happy
spending
to
time
talk about
with me.
exoplanets. Take care.
Thanks so much. Okay, bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.